Okay, good afternoon. I'd like to start by briefly reviewing what was done last time. And what we did last time is to look at several MOSFET IV bulk charge treatment using ion implantation to adjust VT. I think that's really what we did, is using ion implantation to adjust VT. And we talked about body bias effect. That is, VT is a function of the body bias, VBS. And one thing I pointed out is that the first two terms on the right-hand side of the VT expression typically adds to 0, particularly for two cases. NMOS using N plus polygate and PMOSFET using P plus polygate, two normal cases. Qualitatively, we should remember this as the characteristics of the body effect. That is, this DVT, DVBS, the sensitivity of VT to VBS goes up, which is undesirable, but it goes up when the doping concentration is large and when oxide is thicker. I didn't do this right. Okay. Sorry, COX goes down. All right. When COX goes down or when TOX goes up. So the two things to remember is these two, right? When the doping concentration increases, VT becomes more sensitive to VBS. When the oxide thickness increases, VT becomes more sensitive to VBS. All right, and that's undesirable. We don't like that. Okay. By the way, do you know when we see a combination of thick oxide and heavy doping of the body? When do we see that combination? Maybe this will give you a hint. First, ask this. When you do have such a combination, when oxide is thick and the doping concentration is large, what kind of VT are you going to get? Do you get a large VT or small VT? Large VT. So basically, it's when you have a large VT, you get very large DVT, DVBS. So in MOS transistor technology, CMOS technology, when do you get very large threshold voltage? Can you think of any cases when the threshold voltage is unusually large? What's that? Isolation. Excellent. This is called the field threshold, field transistor threshold. So field transistor, it has particularly strong body effect. This actually is sometimes it's very important, both good and bad. The good thing is that if you find out that your isolation threshold voltage is not high enough, a little bit of body bias is going to do a lot of good to increase it. The bad thing about it is that what if your VBS is a positive bias, which sometimes can happen? Not that you deliberately create it, but just because the way the current flows in the substrate, the IR drops, that can forward bias the substrate and the source. When that happens, your field threshold voltage can drop by many volts, and you will lose your isolation, the circuit can fail. So these are the cases when particularly this body bias is or cause unusual problems, all right? And if you're not familiar with isolation, this concept of a field threshold, is probably because you did not read the Chapter 6. Chapter 6, according to the course outline, should be read after we finish the Chapters 3 and before we start Chapter 4, somewhere in between there. I probably should have reminded you. But if you have not read Chapter 6, isolation, then certainly read that. And before you read the chapter, I want you to also remember to look at slide 1-3. Now that's part of my course syllabus. We went through that the first lecture of this course. Now on that slide, I pointed out which sections to read, right? So I'm not asking to read every section of that chapter. So to look at that. We have, at this time, more or less completed Chapter 4, the IV characteristics. And according to the course outline, you should be then reading or start reading chapter 1 and 2. And the topic is device simulation. Okay, last time we briefly mentioned device simulation as the way to calculate the VT for arbitrary doping profile, right? And again, see slide 1-4 for the specific sections to read. I'm only asking you to read a few sections, not this 2 full chapters, all right? Okay, now we did one other thing last time, and I want to particularly remind you, is we also introduced the model, the VT of retrograde well device. And if you recall, the model says that VT is equal to VFB plus 2 phi b plus 2 epsilon silicon phi b Cox over WD max. Now, perhaps there's another term to use here that may be even easier. Yeah, why don't I do this? For this particular purpose, not for comparison, I'll go back to D, all right? D is the thickness of the lightly doped region, all right? So it's VFB plus 2 phi b plus 2 epsilon phi b Cox times D, all right? And we also had some discussion about the meaning of 2 phi b should really be 1 phi b plus a constant, all right? Okay, any questions about what we talked about last time? Okay, if not, let's move on. New section. I think this is close to the end of chapter 4. And it is 4.7, subthreshold current, all right? Now, subthreshold current is a term I think we have actually brought up in this course, and you probably have heard it before. Now, the easiest way to view the subthreshold current is to look at this log IDS versus VGS plot. Log IDS versus VGS plot. We're going to see threshold voltage is somewhere here. Beyond threshold voltage, we'll have more or less the usual linear relationship between IDS and VGS. So on the semi-log plot, we will see a logarithmic curve. Today, we're going to concentrate on this part. Below VT, it can be shown that this curve should be more or less a linear curve. So IDS is exponential function of VGS. The significance of subthreshold current really can be summarized by this phrase here. The important thing is we want to look at the current at VGS equal to 0. At current at VGS equal to 0, IDS must not be too large. In other words, looking at this point, when VGS equal to 0, because of the presence of subthreshold current, IDS is not equal to 0 at this point. Now, that's fine. We can tolerate some leakage current, but cannot be too large as leakage. Now, why is that? Because in a circuit, suppose a CMOS circuit, let's say, all right? One of these two, doesn't matter whether this V in is equal to high or low. One of these two transistors is in the off state. Because it's in the off state, therefore there's no current flowing between VDD and the ground. And we are counting on that to have low power dissipation of the CMOS circuit, all right? That's why we can store a lot of information in the Palm Pilot and not drain a lot of battery. Because when we are not turning on-off the CMOS circuit frequently, we don't drain a lot of current. We don't dissipate a lot of power called standby power, all right? Now, however, even in this case, some current does flow through the device that's off. Let's take the example of V in equal to 0. Because V in equal to 0, this N-channel transistor is off because VGS is equal to 0. When VGS equal to 0, this transistor does not conduct a lot of current, but does not conduct zero current either. It conducts this much current. And that's why we cannot allow this current to become too large, all right? So the most important current is at VGS equal to 0, IDS must not be too large, all right? And for that reason, we talk about subthreshold current, which means it's IDS in the regime of VG being less than VT. And we can use the chart sheet model to look at it. We kind of look at it in an earlier section. And from there, we know that drift current is negligible. So today, we'll kind of derive a simple expression for the subthreshold current. We start with ID equal to diffusion constant D sub n, meaning electron diffusion constant, times W times dq dy. Right? That's the diffusion current. And then just make very simple approximation. The reason is, you will see later, this current is a very strong function of VT, very strong function of VGS. To the extent we don't know VT exactly, or in fact, the kind of accuracy we're going to deal with is we are going to assume this is straight line, and that involves a lot of assumption already, because this portion is really not a straight line. All right. So given all that, we're not going to worry whether it's equal to Qi over L, or maybe it's a factor of 2 larger than that or smaller than that. We don't worry about that. So roughly, we just take the gradient as Qi over L. All right. Qi is taken at y equal to 0 at the source. All right. Okay. Yes.
It sort of seems like the way that you state at VGS, IDS must not be too large, that there's a mathematical reason that has to be, but it's purely for power conservation?
That is purely for power conservation, all right? At least that's the first trouble we're running into if it becomes too large. Of course, if it gets eventually very, very large, then beyond power, circuit functionality will be affected. That is, you cannot ever tell whether transistor is on or off. How can you use it as a switch in any circuit function? But right now, we're concerned about it because it's a power consumption problem. All right?
One more question?
Yes.
Hi. Reducing the subthreshold current is greatly beneficial for the digital circuits.
Yes.
But what do you think, like, for the analog devices?
Then it's not so important. That is correct. All right. But the number of devices using analog circuit is small. The number of devices using a digital circuit can easily be several hundred million in one chip. Now that's where even 1 microamp leakage is per transistor is going to kill you, right? If a 1 microamp leakage per transistor and you have 100 million transistors on a chip, this means the chip is going to take what? 100 amperes, even if there's nothing sitting there, right? And no battery can tolerate that. So that's why we have to keep this leakage current extremely low, right? Okay. Yes?
Usually, when I look at the device parameters, there is some trade-off between the subthreshold leakage amount and the speed, right? So why?
It has to do with this VT trade-off. We'll talk about this later, but just because you brought this up, let me just say that clearly we can make this current smaller if we bring the VT to a higher value. Then this whole curve will shift it to the right, right? It will look like that. Then the leakage current becomes much smaller compared to the original curve. Do you see that? But when we move VT to a larger value, when we increase VT, if you remember the expression for ID set being proportional VG minus VT, or VG minus VT to the second power, then larger VT will reduce ID set. And reduced ID set will make circuit smaller. So say again?
But it requires a higher supply voltage.
What do you mean by requires a higher supply voltage? What do you mean by that? Could you clarify
When
it?
you increase the VT threshold volt, usually requires a higher supply voltage.
And that's definitely a no-no in the sense that reducing power supply voltage is required by the need to suppress or control the power dissipation. All right? Power dissipation, in a way, is the way, at least so far, this discussion is motivated, or we use that as motivation to justify why we want to control this value, is reduce power. Now, if we increase VDD, it turns out the power dissipation of chip also increases because power is I times V, and each cycle of switching CMOS will take certain current. So I is basically, well, in fact, even I also increase with increasing VD. So the power dissipation in the dynamic state, dynamic power dissipation is going to be too large. So we can not take that trade-off, higher VT and higher VDD. We don't want that. All right? Okay. So, well, just because there's several good questions about why we're concerned about this subthreshold, let me just give you another example where we're concerned about it. If you think about the way the memory arrays are organized, whether it's static memory or SRAMs or non-volatile memories, you probably recall that it has to do with a bit line with many bits of memory connected to it, or many transistors connect to it, all right? All right? Yeah? When we want to sense this memory or read the memory, what we usually do is we turn on one of these rows. So turn on one of the transistor. The other transistors connected to this bit line are left in the off state. And we are counting on the fact that these transistors or memory cells in the off states do not draw a lot of current. If they don't draw a lot of current, then we can just sense the state, 1 or 0 state of the cell that we have selected by looking at the current going through the bit line, whether we have significant current going through it or not. If we have a lot of current going through, then we know this memory is storing a bit that's on, right? If there's not much current, that's off. You can see that read operation will not work if each of these transistors, which are not selected, supposed to be off, each conducts significant current. And if we have thousands of these, they added to be the same amount of current that an unstated transistor will conduct, and you will just not be able to read it anymore. See that? So that's another example where we cannot tolerate large leakage current. All right. So there are several reasons we cannot tolerate large leakage current. In fact, I might as well point it out this time. One thing we can actually say is that what makes a transistor as opposed to a resistor, let's say, is the fact that once we put 0 volt on the VG, we can count on this device taking on very little current, no matter what VD we put on this drain. All right? In order, the gate can make this transistor, can turn it off. If that cannot be done, then we no longer have a transistors, and that's why a leakage current is a very important consideration. Right? Okay, so the gate just must be able to suppress the drain current and make it very small. So we're concerned about this current. So ID is equal to dW QI over L, and QI is equal to Q times NS times inversion layer thickness. NS being the volume density of the electrons, specifically electron density at the surface. Right? It's the same notation we used before. Does that make sense? Roughly speaking, it's just approximately. Q times electron concentration on the surface times the thickness of the inversion layer if we knew how thick it is. Is that right? Yes? Okay. So, by the way, if we use the quantum mechanical analysis, how thick is the inversion layer? What would you, okay, this is a little perhaps irrelevant question. Just if you don't look at this question in the context of the subthreshold current, just in general, if someone asks you how thick is the inversion layer, if you answer 20 angstroms, it's a good answer because that's kind of the typical inversion layer thickness if you solve the Schrödinger equation, right? But that thickness is actually a strong function of the gate bias. When we apply a gate bias that's very close to VT, or we're right at threshold, in this case we're actually at below threshold. Of course, the electric field in the substrate is not as large, and the inversion layer is expected to be thicker. All right, so therefore today we're not just going to assume this to be 20 angstrom. You will see what we're going to do. All right, but in strong inversion, if you say it's 15, 20 angstrom, that's a good answer. All right, okay. Now, so it's equal to Q times electron concentration at the surface is equal to MP0 exponential Q phi s over KT. Okay, does this look familiar? MP0 is the equilibrium concentration times exponential Q phi s over KT. That gives us the surface electron concentration. Is that right? Yeah? Okay. Next, we need the thickness of this layer. In other words, over what thickness do we have an electron concentration that's roughly equal to ns? And beyond that thickness, further below into the substrate, and we have much lower electron concentration. So as a result, on average, we say that's the thickness we have to consider. Now this makes sense, kind of makes sense. You take KT over Q divided by the electric field at the surface. KT over Q is voltage. Voltage divided by the electric field gives us distance. Now what's the physical meaning of that distance? KT over Q, that voltage, divided by electric field at the surface. It actually is not debye length. Debye length would not be a function of the surface electric field. What it is this will give you the distance or the thickness, if you will, the distance over which EC would rise by KT over Q. Yeah? In other words, if you look at this energy band diagram, if you take ET over Q, draw a horizontal line, what you get here is the distance we just talked about. That's the distance we just got by that ratio. Does that make sense? You take the voltage drop divided by the field, you get the distance over which you get this voltage drop, right? Now do you see why we call this the thickness of the inversion layer here? This is because when we get to this point, then the electron concentration is no longer equal to ns, but rather ns divided by, what factor of 2.3, is that right? Yes? Right? Yeah? So it's kind of average thickness. Is that right? Even within this distance, electron concentration is no longer uniform at n sub s, right? Decreasing. So roughly. Is okay? All right. Now, do we know what ES is? Do we know what the electric field surface is? Yes, we do. We always go back to the depletion region approximation. That's a very good approximation when we treat the depletion region. And the electric field at the surface is equal to 2q Na phi s over epsilon s. Either you have memorized it somehow. If you have not memorized it, let me just tell you, you can derive this now by Gauss' law. By Gauss' law, the electric field surface should be equal to Q depletion divided by epsilon s. Is that right? And Q depletion, you probably remember, is equal to all these quantities, including epsilon s, in the numerator. I probably shared my mnemonic trick with you. That is, I actually remember in the expression for Q depletion, there's nothing in the denominator. All these quantities appear in the numerator, all right? So when you divide the Q depletion by epsilon s, you get epsilon s in the denominator inside the square root term, all right? So that gives us the electric field. Okay? All right. And that's it. Now we got the expression that we kind of can use, that is ID is equal to Q KT over Q square root epsilon s 2Q Na phi s dNW 1 over L Ni square over Na exponential Q phi s over KT. So kind of expression. Right? The only problem is that, well, we don't know what phi s is. We want to know phi s is function of Eg. Okay? Now this is the same question we've dealt with many times. How to get phi s as an analytical function of Vg. Remember? All right. So this is one approximate solution that we got in chapter 361. We got. But even this is too complicated, and we don't think it's really accurate enough given the approximation we have made elsewhere. So we usually don't even use this equation. We use something even simpler. We simplify this by looking at phi s as a linear function of Eg. In other words, looking at its linear portion. All right. If you use this whole term, then more or less you can model this part, even where it's not a straight line. Do you see what I'm saying? But this is not very accurate anyway, because this assumes that really there's no inversion layer charge, and this is all due to the depletion charge. So when we get close to VT, we still don't know how to deal with that. All right. So given that fact, and the fact that this looks pretty much like straight line, so it seems it's not worthwhile to model this with anything other than a linear relationship between phi s and Vg. In other words, exponential relationship between IDS and Vg. So we're looking for a linear relationship between phi s and Vg, which will give us exponential relationship between Vg and IDS, right? That's what we're looking for. That's very easy. You can always do this with some kind of let's say, a Taylor expansion. But normally, we don't even introduce the final result by invoking the Taylor expansion. We simply quickly go to a simple approximation. Approximation happens to be very good approximation for retrograde doping again. All right, that is, we just don't consider this depletion layer thickness to vary with any bias voltages, not even as Vg. Let's assume there's a fixed WD max. In other words, the C depletion is fixed. All right? If we make that assumption, all right, then the relationship between phi s and Vg becomes quite simple. And in fact, I don't think it's worthwhile deriving that. So I will, I guess I did not derive it. So let me just remind you what we have before. What we have seen before is that phi s is really a linear function of Vg after Taylor expansion or after using this voltage divider concept. It's really equal to some constant plus, okay, I'll finish this, plus this, if you remember, Vg divided by 1 plus C depletion over Cox. All right? In other words, if we plot phi s as function Vg, we get a slope that's smaller than 1. For 1 volt change in Vg, we don't get 1 volt change in phi s. We won't get a fraction of a volt change in phi s. And that fraction is this. Is 1 over 1 plus C depletion over Cox. Okay? It's because the voltage Vg is divided between two capacitors to give us phi s. This is the delta phi s. This is delta Vg. If we apply delta Vg, only a portion of that shows up as delta phi s because we have two capacitors divides this delta Vg. Right? So delta phi s is between delta Vg and 0 and the ground. And the division, that factor, we have seen this before, is 1 plus C depletion over Cox. All right? Can you see that? Okay. So we're not going to go through this equation again. Instead, let's just look at this. Suppose it's a straight line. Suppose this log IDS over VGS is a straight line. Then we define something called subthreshold swing, something called swing. What swing is really this. We can ask a question. How many millivolt of reduction in Vg? How many millivolt reduction in Vg will bring about 10 times reduction in ID? And any times we see a straight line in a semi-log plot, we can always ask this question is, what does it take in the change in Vg in order to reduce IDS by a certain factor? And we choose a factor of 10 here in this question, all right? So how many millivolt reduction in Vg will bring about 10 times reduction in ID? To answer that question, the answer is swing, and swing is equal to d log ID over dVg. Take to the inverse of that. Okay, don't bother to look at over this equation now. That's not worth the time. Just concentrate on this figure. I think graphically it's easier to understand what swing is. Right? Swing is nothing but how many millivolt does it take to reduce IDS by 10 times. Suppose the answer is 90 millivolt, given a particular slope of this plot, then another 90 millivolt reduction will reduce IDS by another 10 times. Another 90 millivolt reduction in VGS will reduce the IDS by yet another 10 times. All right? Okay. So the swing mathematically can be shown as d log ID dVg. Take to the inverse of that. Now, using the equation that we have from the previous slide, I will not show you again, but in the previous slide we know this is a function, exponential function of phi s. In fact, it's proportional to q phi s over kt. All right? So just differentiate this equation in the previous slide for ID, we'll end up with this. It's equal to the natural log of 10 times kt over q d phi s dvg, inverse of that. Okay? And the natural log of 10 times kt over q gives us 60 millivolt. This is because kt over q is about 26 millivolt. Natural log of 10 is something like, what, 2.3 or something like that? So when you multiply the two together, you get 60 millivolt. And this is a very important number to remember. 60 millivolt has a very important meaning in the and large significance in the device physics. All right? So 60 millivolt, let's remember that. Times 1 plus C depletion over C aux. What this means is that it will take at least a 60 millivolt reduction in VGS in order to reduce IDS by 1 decade. And we want the swing to be as small as possible. The reason is a small swing will allow us to design a transistor with very low VT and also very small leakage at VGS equal to 0. Do you see that? If the slope can be small, I'm sorry, the swing, sorry. Swing is not slope. I should not use this two terms interchangeably. I made a mistake. Swing is the inverse of the slope. All right? So we want the slope to be very large. That means we want a very small swing. Because if the swing is small, slope is large, then we can design a transistor with small VT and still satisfy the goal of low leakage at VGS equal to 0. And the small VT will give us high speed, high performance. All right? That's what we really want. So we should always be rooting for the small swing. Because we're rooting for a small swing, the first thing we recognize is that we cannot design a transistor with swing any smaller than 60 millivolt. If we can get 60 millivolt, we're very, very happy. All right? We always get a swing larger than 60 millivolt. Larger by how much? Theoretically, by this factor, by a factor of 1 plus C depletion over C aux. And it's larger by that factor because of this voltage divider. What that means is that in order for the current to be very sensitive to VG, we want phi s to be very sensitive to VG. In order for phi s to be sensitive to VG, we need to do one and or both of these following two things. That is, make C aux very large or make C depletion very small. Does that make sense? If we make C aux very large, then we can change delta phi s as much as 1 millivolt per millivolt of changing delta VG. Similarly, if we can make C depletion very, very small, such as no C depletion, 0 capacitance, again, delta phi s will change with delta VG 1 volt by 1 volt. In that case, we'll get 60 millivolt. Otherwise, it requires 60 millivolts times this change in the VG before delta phi s can change by 60 millivolt, and that is our swing. Okay? All right. So to reduce ID by 10 times, phi s must be reduced by at least 60 millivolt. Let me just say at least 60 millivolt, right? By at least 60 millivolt. I'm sorry, phi s, sorry about it. Here we're talking about phi s, so there's nothing wrong. To reduce ID by 10 times, phi s must be reduced by 60 millivolt. Therefore, VG must be reduced by 60 millivolt times this factor. All right? Okay. Yes?
What's that little box?
The little box, did you say?
Yeah, in the box.
What's in the box? Oh, in this box here. That's probably, they should not be there, all right? So this should be deleted, this box. There's nothing in that box. Okay. All right, the typical requirement for this leakage current, how much leakage current can we tolerate? Well, that number has been changing. Used to be that we really don't want to tolerate any leakage larger than picoamp. Now today, for many applications, we still want to hold to that. Perhaps a DRAM, because of the refresh current requirement, we don't want to lose the charge rapidly, so we want to hold the subthreshold current very low. For handheld low power applications, we want to hold them to very low power, all right? Low leakage. On the other hand, for high-speed applications where we really want to design a transistor with as small VT as possible so that we can get high speed. And then we're willing to tolerate more leakage. And today, 10 nanoampere of leakage per micron width of transistor is not considered large. If you look at the roadmap, a few generations down, we're probably going to tolerate 100 nanoamp per micron, all right, or 0.1 microamp per micron. But today, I would say these two are two good numbers to remember. For low power and low leakage application, by low power, I really should mean low standby power application. Every application we want low power, but very low standby power handheld type application, we are still looking at current as small as picoamp per micron of leakage. All right, maybe 10 picoampere. For a high-speed application, we're willing to tolerate 10 nanoampere per micron of W. Okay, that's typical. Is that okay? All right. Now, what is typical for swing? What is typical ratio for this, in other words? Well, typically, we get about 80 to 90 millivolt of swing. Now, fortunate thing is that as a result of scaling, COX has been scaled very aggressively. As a result, we are not seeing swing increase. If anything, might have creeped down a little bit, but more or less maintain the uniform. The reason is we also have been reducing the depletion region thickness, WD max. One reason, last time we mentioned, is because the control short channel effect, right? We have to use small WD max. So we're not really getting better swing either. So that pretty much maintained this value, okay? So these are typical values, okay? Let's see, and finally, if swing is fixed, if this is fixed, that pretty much tells us what VT is required. So as a result, today we're dealing with about 0.5, 0.4 volt of VT. In the future, maybe we'll look at 0.3 volt of VT. All right, so that's kind of a range we're talking about. And beyond that, everything is fuzzy. It's not very clear how much we can reduce VT, how much more leakage current we can tolerate, and so clearly there are some circuit techniques going to be applied to control this leakage current. There are device technologies that will be introduced, and we can talk more about this as we go on. One thing is that the technologies will provide transistors, several different kind of transistors in a given technology with different VTs. So let's say all the transistors will, shall we say, be designed with the high VT transistor, let's say 0.5 volt. So you have designed this circuit now. As a result, leakage current is very low. Is that right? Then you look at the critical path, because there are only a finite number of paths that really limits the speed of the circuit, right? Critical path. And there you figure out, hey, if I selectively reduce the VT of these 200 transistors, then the circuit speed can be boosted, right? So I will use the low VT transistor for those. You see what I mean? But because the number of those transistors are small, if each of them take 1 microampere, it doesn't matter too much. You see what I'm saying? If the other 100 million transistors take very low leakage current, this 100 transistors, I can allow them to take 1,000 times larger leakage current. Is that right? So this is the concept of multiple VT technology, right? That's not too expensive to do. And so things like that is beginning to be to come online, all right? But we're right at juncture when these are beginning to come online. All right, another kind of interesting question we can ask, given the knowledge we have, so at VGS equal to 0, what kind of surface concentration are we talking about? you may have not thought about this. That is, in the so-called off state, when VGS equal to 0, are we, in weak inversion? Are we below weak inversion? Is electron concentration larger than Ni, smaller than Ni? What is the electron concentration, right? Okay, we can estimate that right now, shall we? We know that, let's take 1 picoampere as the current for this 1 micron wide transistor, right? Picoampere, I'm taking the low state. All right, just for fun, later we're going to change to 10 to the minus 8 to see what we get. That's all right? But we start with the picoampere. Is okay? That's our ID. And it's equal to Q dN over L ns T inversion W. All right? W, we know we're talking about 1 micron, right? Because we're using the current per micron here, 10 to the minus 12 ampere per micron. Yes? So W is 1 micron or 10 to the minus 4 centimeter. Well, what we know, Q is 1.6 times 10 to the minus 19. Do you remember what's the typical number for diffusion constant? All right, just order of magnitude. If you tell me 10, that's a very good answer. All right, if you say, 30, it's okay. 5, it's 3, that's okay. All right, 10 centimeters square per volt per second. Channel length, let's use 0.1 micron, which will be 10 to the minus 5 centimeters. Okay. All right. Inversion layer thickness, I'm using 100 micron, or 10 to the minus 6 angstrom. Why did I not use 20 angstrom? Why did I use 100 angstrom? Because we're not in strong inversion, we're in subthreshold, right? In subthreshold, electrons are not pulled as close to the surface as you would think in a strong inversion case. Is that right? Okay? All right. So put these numbers in. 10 to the minus 12, 10 to the minus 5, and 10 to the 19, 10 to the minus 6, 10. Where does 10 come from? What is 10 to the minus 4 is this one? 10 to the minus, oh, this must be 10 to the minus 5. What am I doing here? All right, let's do this again. 10 to the 10, okay, there should be a, all right, let's do it. 10 to the minus 12 is this term. Oh, I see. This is the 10 to the minus 5. Okay, why don't we just do this right? Okay, what are we talking about? All right, so this is 10 to the minus, okay. Jeez, I don't know what happened here. Let's redo this, all right? Let's just totally redo this. All right, let's totally redo this. How does this happen here? All right, let's forget about the 10 to the minus 1.6. So I have 10 to the minus 19 here, right? Is that right? We got that, right? So D is 10 is 10. Oh, is it possible that this is so inverse? No, it's not inverse. All right, so D is 10. Let's do this. And then we have the NS. Oh, I'm sorry. What I'm talking about? We're looking for NS. I'm sorry. We're looking for NS, right? So I move NS to the left-hand side. I beg your pardon. Move NS to the left-hand side. So right-hand side, we are left with ID, the 10 to the 12, times L. That's 10 to the minus 5, divided by all these. I beg your pardon. So divided by 10 to the 19, 10 to the minus 6, so on and so forth. So we get 10 to the minus 17, 10 to the minus 28, 10 to the 11th. Okay, so they conclude. So for low power devices, this is right at inversion, I guess, right? So you just get a little bit of electrons here. By the way, this is extremely small density of electrons, surprisingly small, perhaps. All right? Okay? To appreciate how small it is, maybe I couldn't tell you this. But just for fun, maybe we'll do it together, all right? This is the 110 to the 11th per centimeter cube. If we multiply this by the electron inversion layer thickness, right? That will give me the number of electrons per area, right? Per centimeter square. Is that right? And what is that? That turns out to be 10 to the 5 per centimeter square. Is that right? And if I multiply this by W and by L, what would that give me? Total number of electrons, all right? Let's take, we said it's 1 micron W, right? We said it's 0.1 micron of L. So that's 10 to the minus 9 centimeters squared, is that right? 1 micron of W, 10 to minus 4. 0.1 micron of L, 10 to minus 5. Is that right? Yes? So how many electrons are we talking about per transistor? Can you give me a number? 10 to the minus 4 electrons. Can you even visualize how this works? But this is the kind of number we're dealing with. Really surprising. But that is responsible for the leakage current we're fighting for. We're fighting against. That's what it really is. So another interesting thing is when we put an ammeter there, when we put a current, voltage between source and drain, what's the average electron in transit if you take snapshot? And that number is also this. All right? So this really reminds me of some experiment where what is it, silver ion was made to pass through a slit looking for diffraction. Isn't that right? So there must be some interesting things we can look for when current is in such a low range. But that's exactly the kind of number we're dealing with today. All right? We're looking at fractional of electrons in the transistor at a given moment. And that can even give us problem in the behavior of the transistors. All right? Okay. Now, if we're talking about the high-speed transistor, low VT transistor with leakage current that's 4 orders of magnitude larger than the example we used, then we'll be talking about what? 10 to the 15th, right? That's also kind of a good number to remember. So we're definitely not talking about no electron in the surface, even though we're in off state, right? So it's not surprising we could be having a leakage problem if we have 10 to the 15th of a transistor of electron concentration. Is that right? All right? So even in VGS equal to 0, even we call the subthreshold, we still have plenty of electrons, right? Okay. Any questions? All right, if not, we have finished discussion of the subthreshold current, right? So we'll move on to the last section in this chapter, 4.7.2. That's called the gate-induced drain leakage. That may be a new topic for for many of you, and actually I coined this name, and the acronym is called GIDL, G-I-D-L. And before I go on, let me just say it's believed to be, now we understand it's due to band-to-band tunneling. So sometimes you hear the name band-to-band tunneling, right? BTBT is another name sometimes used in the, okay? Band-to-band tunneling stands for this mechanism, all right? Okay. This leakage current is observed in this case, and I think that is why this particular textbook introduced this topic right after subthreshold current. It's kind of a reasonable way of organizing the topic. In a sense, it is also a subthreshold current, although people do use these two terms to refer to two different mechanisms. So subthreshold current referred to the mechanism we just finished discussion. This one, although it happens at VG sub VT, it's best not to call what we're going to speak about now, call that subthreshold current. You know what I'm trying to say? All right, it is subthreshold, but the term has a pretty specific, let's say, tie to that particular mechanism we just finished talking about. So for this leakage mechanism, it's called a gate-induced drain leakage, GIDL or GIDL. We see this in the same plot, log ID versus VG. This is the inversion region, this is the subthreshold region. So we do see current decrease with decreasing VG. But at some point, the current starts rising again. Now this, of course, is a problem if we cannot understand or control this. Because if we cannot understand or control this, then, doesn't help. Even if we make VT very large, we're still going to get large leakage current. In fact, you get maybe even get larger leakage current, assuming the whole curve moves with the VT. But I haven't told you what determines this. So we don't know what this portion will move with changing VT or not, right? All right. So we're not going to be able to suppress it just by making VT larger. So what is responsible for that? And I think that maybe it's fun to mention. After we have published this research. More than one person told me that, we have seen this long time ago. We just thought it's a, leakage in an electrical cable or something like that, did not pay attention to it. So the moral, I think, is that a good experimentalist will never take anything for granted, right? Usually, very important discovery is made just by accident, by noticing the details. So turns out this was not a leakage in the cable. It's quite reproducible, and once you think about it, it's not too difficult to understand. We understand today that this happens in the region where the drain and the gate overlap, all right? So this is a cross-section of MOS capacitor. I'm directing your attention to this portion where you see the gate electrode, you see the gate oxide, you see the drain diffusion region that we call M+ here. Is that right? Okay? And let's remember, the bias under which we observe this current is Vg equal to 0. I'm particularly looking at one point here, right? Of course, this model will also apply for other VGs, but let's just assume Vg is equal to 0 right now. Just make it simple, all right? Okay. And it's also observed that this current increases with increasing VDD. In other words, we do have to apply VDD to this for just to show. If we only apply, say, 10 millivolt VDD, we won't see this current. If we apply 2 volts, we're going to see this current, 3 volt, even larger, such a leakage current, all right? And so VDD is applied. VG is ground. It's okay? That's the bias we're talking about. Now, concentrate on this portion again, looking at this dotted line that I just drew. Okay, look at that dotted line. Along that line, can we draw the energy band diagram along this dotted line? Okay, this vertical line. Let's draw the energy band diagram. First, you will realize this is an MOS system, right? MOS capacitor, MOS, right? The substrate is M+ silicon. Is that right? Right? Now, is the gate more positive or more negative relative to the substrate? This is an N-channel transistor, so VDD is always positive, right? And gate is ground. So gate is more positive or more negative than the substrate. By substrate, I'm pointing to the M+ string, of course, right? It's more negative. Is that right? So the energy band diagram should be drawn this way with the gate high, gate side high. Is that right? Because it's more negative. Is that right? Next, I did not draw this as band bending as saturating at 2,5B. Why is that? I allow this band bending to be larger than 2,5B. Why is that? Right, because there's a so-called body bias, right? This is the body to source bias. Don't call which source was body, it's confusing the name. But the fact is, anytime you have a PN junction there, right, nearby, with reverse bias, you know that the inversion will not happen at 2,5B anymore. It's going to happen at 2,5B plus VDD, okay? And by the way, before we even reach that kind of band bending, something else happens, namely this happens. So we'll not even reach 2,5B plus VDD. It's just that we will not be limited. Band bending will not be limited at 2,5B, that's all. Can easily go beyond 2,5B. You remember why, right? It's because of the presence of a reverse bias PN junction, because it's a body bias. We get now 2 Fermi levels. And the 1 Fermi level that determines the electron concentration, hole concentration in this case, to determine the presence of the inversion layer will require the band bending to be much larger than 2,5B. All right? Okay. Another way to understand that really is this, is that we will never be able to establish an inversion layer because anytime you have holes here created maybe by the thermal generation, what will happen to that hose? Hose will simply flow out. Because if you look at the bias, this being more positive, the body side is being negative, the hole would simply flow in this direction, would just flow out. Okay? Now that's enough for our discussion today. But just for those of you that are really interested in this kind of discussions, in details, actually there are special cases where you can ask questions. Is it possible to design a potential profile such that there's a dam against the hole flowing out. If so, then there will be an inversion layer. If there's inversion layer, band bending will not C25B. Okay, I will not pursue this line discussion anymore because we don't really need that. But just set this as a let's say extra question for those of you that want to think about this to think about. But because band bending can go beyond 25B, it can certainly go beyond may go beyond say VG. And when that happens, a very interesting situation happens. If the band bending is larger than Vg, that means some of the energy states in the valence band now find energy states in the conduction band lined up with it, which means tunneling now can happen between the valence band states and conduction band states. Do you see that? Whereas if the band bending was limited to 25B, as we usually draw, there's no way for any electron in the valence band to tunnel to a conduction band. Is that right? But because the band bending can go beyond the EG, electron now can tunnel from valence band into conduction band. That's why it's called band-to-band tunneling. Is that right? Got it? Okay. So this bias, first of all, condition, this MOS arrangement allows band-to-band tunneling, first of all, because band-band is larger than EG, therefore we can have band-to-band tunneling. Next then becomes, how large is this band-band tunneling rate? Because this band-to-band tunneling creates current. Maybe I should explain how that happens. When an electron tunnels to the conduction band, from valence band to conduction band, what does that mean? That means once this electron is created, conduction band electron is created by the tunneling, this electron will simply flow out into the drain leads by conduction, because the polarity and the field is such that electron will flow out of the drain. It will leave a hole here, and the hole, as we said earlier, will simply flow out into the substrate, because the polarity is very reasonable. Okay? So first of all, we now see that this band-to-band tunneling leakage current flows between the drain and the substrate, not between the drain and the source. All right? So that's an easy way to separate these two mechanisms. If you see some current here, you don't know whether it's due to the subthreshold leakage or due to the Guido current. Well, just to measure, don't just measure the current flowing into the drain, but also measure IS and measure IB. The IB part is the Guido part. IS part is the subthreshold leakage. The sum of IS and IB better be equal to ID. Otherwise, you discover the exception to Kirchhoff's law, right? So it's always good to measure several currents at the same time, all right? Okay. So therefore, the tunneling rate determines this Guido current. What determines the band-band tunneling rate? Well, it turns out this is also known, and the equation was first derived for the tunnel diode, or also known as Isaki diode. Leo Isaki received the Nobel Prize for studying the band-to-band tunneling semiconductor, and that is the tunneling current should be equal to a constant exponential minus a constant over yes. And these A and B's are known analytically in textbooks. Often you will find that those expressions, I think our textbook may or may not have given them, but they are often given in terms of Planck's constant, the effective mass, and band gap, and things like that. There's a problem in theoretically predicting B, because it involves the effective mass. And it's not clear what the effective mass is when the electron is tunneling in the bands. You know, when it's in the valence band, we know the effective mass. When it's in the conduction band, we know the effective mass. But when it's tunneling through this band, we actually don't know what the effective mass. So this is a little bit of a problem determining that B. In the past, B was determined experimentally by looking at heavily doped P plus N plus diode, looking for the band-band tunneling in P plus N plus diode. But you know, think about the difficulty of determining the electric field for given a diode. we don't even know the doping profile very accurately. You can imagine. This only happens in a region about 100 angstrom, the tunneling region. So how do you know the electric field? So it's always a problem. It turns out this technique of studying Gödel can determine the electric field quite simply, I will tell you, and such that it actually, I believe, gives the best number for this B, and which corresponds to about 0.5 as the ratio of the effective mass to the free electron mass. All right? So I will show you what determines the electric field, the ES. That's the remaining question. But before I show that to you, why don't you think about it, all right? So A and B are already known theoretically as function of E, G, and M. So the only question is ES, the surface electric field near the surface, at the surface. How would you determine that? Now, if you start thinking about, Q depletion over epsilon, that's very good. I congratulate you about that. The problem with thinking along that way is that you will still have to know what the doping profile is. That we also don't know. Okay, we cannot simplify the problem too much. Cannot just say, I know it's 10 to the 20th. Maybe it's 8 times 10 to the 19th, maybe it's not. And what is it? We don't know, right? So any other way to get yes? Suppose I take this option away from you. How do you get an estimate of a surface electric field? All right. What if you're asked to estimate the oxide electric field? What would you do? Let's remember, this is just between gate and M plus semiconductor. Cannot be that difficult, right? All right. So this is what one might do. All right. This may not be the only thing you can do, but this is one thing certainly one can do. Okay. All right. So the question is, ID equal to A exponential minus B over epsilon S. Can we express ES in a way that we can actually use in some real manner, rather than just a theoretical concept that if we knew ES, we know ID? How about try this way? ES is equal to the oxide field divided by 3. Does that make sense? 3 being the ratio of the two epsilons. Huh? So if we knew the electric field in the oxide divided by 3, then we know the electric field in the silicon. Is that right? Right? Electric field in the oxide, does that make sense? Is equal to the voltage in the oxide divided by oxide thickness. Is that right? So the question is, what is voltage in the oxide? Well, voltage in the oxide, we know is always equal to VGD minus VFB minus phi s, band bending. Right? We're using the same old equation, in another new problem now, right? Right? Instead of calling that VGB, I guess we call it VGD because our substrate this time is the drain. Is that right? Right? So VGD minus VFB minus 1 minus phi s. The problem is always not knowing what phi s is. But after thinking about it, maybe looking at the simulation a little bit, one can determine actually, 1.2 is not bad assumption, 1.3 is fine. In other words, if it's only 1.1, we know we don't have band tunneling, won't happen. So as soon as we start have tunneling, allow tunneling, a lot of electron states, we think significant current can happen, and the current will now be limited by this ES, right? So VGD minus VFB minus 1.2 volt divided by 3 TOX becomes a very simple engineering model. We certainly know what VG is. We know what VD is, right? We better know what VFB is. We know the oxide thickness. And then substitute into that, we will be able to predict ID. Okay? So it works quite well. So that's the model for the Gödel current, also known as band-to-band tunneling. And it's just another mechanism of leakage. And sometimes people do call that subthreshold leakage. I think it's acceptable, depending on whether you want to, use subthreshold leakage in a narrow meaning or in a wide meaning. All right. So just another component of leakage current. Okay. Any questions? Yes.
Is VFB like approximately 0 in that because you have an N plus gate and an N plus? So it's not the same VFB that's...
Excellent. So for the standard device, again, we can eliminate this. So the model is even simpler. Okay? And However, here's again interesting question for you. If we're talking about N plus poly PMOS, all right? Now, do we have an easier time dealing with Giddo, or do we have a harder time dealing with Giddo, right? So that's where you have to look at the sign, VFB, and things like that, right? Certainly a question. A question here.
Yeah, I'm just wondering if there's no overlap between gate and source and drain. Is there still, Giddo effect at all?
If you truly can not have the overlap between the source and drain, then the answer is that, I'm sorry, between the gate and drain, then there will be no Giddo. All right? But to make that discussion more interesting, why don't we look at this in a little detail right now, then we will see what that means, what that answer means, all right? All right. There are some approximations, assumptions used in this model, and we can sort of kind of examine these assumptions a little bit, all right? Interesting question is this. You notice in this analysis, the doping concentration of this N plus region does not appear. All right? Now I want you to sort of think about this N, D as a variable. All right? Okay? It may be 10 to the 20th, maybe 10 to the 19, maybe 10 to the 18, and maybe even 10 to the 17 LDD, or maybe 10 to 16. Just theoretically, suppose ND is variable. All right? Is okay? I want you to answer this question for me. Suppose I'm trying to suppress this Giddo, all right? Meaning I don't want to have Giddo current band-to-band tunneling for a given voltage applied across G and D. Should I choose a very heavy doping, or should I choose a very light doping? Suppose I'm trying to suppress this Giddo problem. Now, you suggest to choose a light doping. That's an interesting answer. Give us a little discussion. Why light doping will suppress the Giddo phenomena?
I just thought that you might need apply more negative gate voltage to introduce the Giddo effect.
Very interesting, yeah. If we apply a very light doping, it's almost like, lightly doped substrate, our usual concept of MOS now, more like it. In that case, there's no reason for, when that happens, the electric field at the surface is fairly low. Yes, okay, so if we make ND small, if we make ND very small, it will give us very small yes, is that right? Remember, if the doping is light in the substrate, and if only band-to-band by 1.2 volt, if I ask 1.2 volt, right? And if doping is light, then the electric field at the surface is actually very small. Do you agree? You agree? Yes? Right? So if you want to have a larger electric field, you better band-to-band even more than 1.2 volt. Then you have to apply larger VDG. Now this means Giddo is not too important, right? It won't happen until you apply very high field. Anyone have another answer for me? Yes?
Looking at the band diagram, if you dope the N plus even more, then you have to bend the bands more in order to get into the tunneling region.
Why do you think we need to bend the band more if we dope the drain more heavily?
Well, it just moves the Fermi level up a little bit closer to the conduction band, and you have the probability of an electron state being filled is proportional to what the energy difference between whatever band and the Fermi level. So if you can squeeze
it's very interesting discussion, and that's probably a little more than what I would like to get into, but I can perhaps even further amplify what you're saying. Let's think about a special case of degenerate doping. Some of you may know we can draw the energy Fermi level even above the EC. In that case, we'll claim all those energy states below the Fermi level is no longer available as a receiver, as tunneling, because they are field. For that reason, we'll have to bend a little more. That is true. But what that probably means is that instead of 1.2 volt, we need 1.3 or 1.4. That turns out to be a not large number. So we're not really looking for that, all right? I am hoping, looking for some argument why if we dope the semiconductor more heavily, we can also suppress this band-to-band tunneling. Any ideas? Any suggestions? The question is, how much VGD we need in order to cause 1.2 volt of band bending? Now, if we dope this substrate more heavily, it's going to need more voltage to bend the band, isn't that right? It needs a larger VDG to cause the band bending. In other words, if the doping is infinite, can we bend the band at all? If there's infinite doping, can we actually bend the band at all? It's a perfect metal. Can we bend it? No. So certainly need more voltage to bend the band by 1.2 volts if we dope the semiconductor more heavily. Is that right? Is that right? So we could also suppress this Giddo problem by using large VD, because that means we end up with very small band bending, small phi s, in fact specific less than VG. In that case, that we will not have Giddo problem. Is that right? Yeah? So what's really interesting is that you can show that there is one particular doping concentration that give you the minimum VDG to create a certain ID. And that number is somewhere around 10 to the 18th. That seems to be the worst case doping. All right? All right? But interestingly, is that the drain doping is never constant. Even if you dope those to 10 to the 20th. What does that mean? That means here's 10 to the 20th, here somewhere 10 to the 19th, somewhere 10 to the 18th, somewhere 10 to the 17th, right? Because there's always that gradient. So you always find a place where the tunneling will happen first. Is that right? So when we give you this model, we're already assuming that we're looking at a worst case, worst doping case. All right? So this is a little long answer to that question earlier. What if the drain does not overlap of this of the gate? So suppose, for example, we have LDD. If the doping concentration LDD is only 10 to the 17th or 10 to the 16th, we believe we can significantly improve the Giddo situation, because we're in case 1 now. Very small ND. We'll have to bend a lot. We need more voltage. Right? But unfortunately, that's not a very practical range to work with. That will hurt our ID set too much if we dope the LDD so lightly. You follow what I'm saying? Increasing the drain doping is not a solution, because even we increase to 10 to the 21st, somewhere in the drain we're still going to have 10 to the 18th. You see what I'm saying? Okay. So this definitely is not a solution, right? So here, that's kind of the answer. If you truly don't have any overlap, there's no Giddo. But if you have LDD, you say, you know, I still have some drains, not so heavily doped. Then there's this trade-off, such that we actually do believe, it's known that actually using LDD will somewhat suppress the Giddo somewhat, okay? And part of it has to do with the lateral field. Due to the doping gradient here, turns out there's a strong lateral field as well, simply because phi s is not constant along this lateral direction. If phi s is not constant, then you will have a lateral electric field. And tunneling happens, doesn't matter which direction field it is. Vertical field, horizontal field, the total field will just tunnel in the direction of total field. So it turns out it's known that we cannot tolerate, for example, a very sharp, just arsenic junction. If we do that, Giddo is more severe, and we like to have more graded junctions, so LDD tends to help with the Giddo as well, all right, just by suppressing this lateral field. Okay. So today, of course, we are not giving into the detail. I did give you a reading assignment. If anyone brought this handout volume 2, I can particularly tell you which one it is. If not, let me just tell you. I think the author's name is Jen Chen, I think. And so read that paper. That's reading assignment, all right, in the volume 2. So read that. It has to do with this Giddo current, gate-induced drain leakage current. Other questions about Giddo? All right. we have just finished chapter 4. We start chapter 5, and I'll just introduce. Yes, you have a. Let me just introduce chapter 5. Chapter 5 is the most important chapter of this course, and this may not be the title, the textbook use, but I'll interpret it this way. It's really just a series of advanced MOSFET topics. And 5.2 to begin with, talk about short channel effect. Later, we're going to talk about more accurate models of the transistor IV. All right. But the first topic we'll be talking about is called a short channel effect. And speaking about short channel effect, that term also can mean many things, different things for different people. To begin with, let's just concentrate on this one narrow meaning of short channel effect. Short channel effect simply means VT depends on L and VDS. Sometimes people even want to only consider the VT dependence on L and call that a short channel effect. I think that's a little bit too limiting, but you do see that usage sometimes. So I would say the fact that VT depends on L and the fact that VT depends on VDS all can be called short channel effect. But especially the fact that VT depends on L is known as a short channel effect. Graphically, it can be illustrated this way. We plot VT as function of L. In other words, we take 5 transistors with 5 different channel lengths. Right? They are made of same oxide thickness. They made the same body doping. It's just that these 5 transistors have 5 different channel lengths. And we measure the VT. We're going to find that indeed VT is not a function of L as expected, if L is long enough. But when L is small, we find VT start to drop with the decreasing L. All right. So VT decreases with decreasing L. And that's known as short channel effect. A newer term, I think is a very descriptive term, is called a VT roll-off. So if you call this behavior VT roll-off, I think it's very good. That leaves a short channel effect as being available to refer to a wider range of topics, because many things can be called short channel effect. So this is VT roll-off, all right? Also called short channel effect. And this VT roll-off, furthermore, is more severe when we apply a VDS. When it's VDS, then VT rolls off earlier. Now, why are we concerned about VT roll-off? Because VT roll-off pretty much determines the minimum length of the transistor we can use. What determines channel lengths are 2 things. One, of course, is the lithography. We can just not make the gate smaller than a certain amount, then that's one thing. The other is that for a given transistor design, for this channel junction depths, for this gate oxide thickness, with all effort the device engineer put in to design the transistor, then there's still a minimum length below which the transistor just will not meet certain performance spec. And that is usually determined by this VT roll-off. And the performance spec it will not meet when the channel length is too small, turns out is what we just finished talking about, namely the subthreshold current. Because as channel length gets too small, VT gets too small, what happens to leakage current at VG equal to 0? Gets too large. Is that right? So for this reason, even if the lithography was not a limit, there will be some limit that we can use. We have to put on this L, all right? And so that is a limit, okay? And by the way, today, very often, even in commercial production, our L is no longer determined by lithography, because we can do other things just with that particular layer of lithography called the gate length. We do things like etching of the photoresist pattern. By putting the photoresist pattern in a plasma, oxygen plasma, we can actually make the photoresist pattern thinner. As a result, we can actually beat the optical diffraction limit of the lithography machine. So we're still then limited by the device physics, which will be this problem. All right? Okay, so this is definitely a real limit. So we have to, and the challenge for designing shorter channel transistor is really the challenge to control this problem, deal with this problem. It's an important problem. All right? Now, what's causing VT to drop as channel length decreases is known. The mechanism is called DIBO, drain-induced barrier lowering. So that's another useful name. So DIBO is the reason for VT, this phenomena called VT roll-off, and this phenomenon is sometimes known as short channel effect. Right? So this DIBO can be appreciated using diagram like this. Let's review what happens at VG equal to VFB if we apply a flat band voltage, let's say. Suppose we apply flat band voltage, right? Then the barrier is exactly equal to 0.9 volt, the built-in voltage between M plus and P body. Is that right? Which is roughly 0.9 volt. So if we draw the energy band diagram, we should draw 0.9 volt as the barrier, right? Yes? Because of this large barrier, there will be no electron flowing between the source and drain. And that makes sense. That's agree with our understanding that when VG equal to minus 0.9 volt, there will be no current flowing between source and drain. Now I want to emphasize the interpretations because of large barrier. Next, I want to ask you, what is the barrier when VG is equal to 0? Rough number, based on something we talk about in this first half of today. Hopefully you have a concept. What is happening? What is band diagram like? What is this barrier like at VG equal to 0? By the way, we are plotting this red along the surface. I didn't say that. We're just drawing energy band red along the surface. Okay, I'll change the question. At VG equal to 0, what's the typical value for NS, the surface electron concentration? Okay, 10 to the 11th. So now can you answer me the question, what is this barrier height at VG equal to 0? Half the band gap is a very good answer, right? But if you're dealing with a high-speed transistor, VT is lower for whatever reason, you have 10 nanoamp leakage at VT equal to 0. What is the barrier height? Whatever corresponds to 10 to the 15th electron concentration, right? Which happens to be about 0.3 eV. So that's kind of barrier we're talking about when VG equal to 0. Is that right? Okay? Now finally, when VG is equal to VT, what is barrier height? What is barrier height when VG equal to VT? Okay, a good concept is when VG is equal to VT, NS is equal to 10 to the 17th. We kind of used the number last time, right? As a new definition of VT, right? And in that case, the barrier height is 0.15 volt, all right? So it's good to think this is the picture at VT. Okay, 0.15 volt barrier. Are we okay? All right. So now I want you to relate this together. Now what does VT mean? VT means, okay, so VGS equals 0, barrier is about half of the EV, half VG. At VGS equal to VT, barrier is about 0.1 or 0.15. That doesn't matter. So VT, the meaning of VT is whatever VG that's needed to make barrier equal to 0.1 volt. It's called VT. Can you accept that? All right, you can accept that. Very good. Now that you have accepted that definition of VT, can you see why, to the first order, VT should not depend on the channel length? In other words, if you draw this channel length band diagram again, is there any reason just by reducing the channel length, we somehow reduce this barrier height? There's no reason, right? If we reduce channel length, the thing just look like that, right? The barrier height is still the same, doesn't change at all, right? Is that right? So this is why VT does not vary with L. Now, however, can you see that if we make the L much smaller, even smaller, at some point barrier height will be affected by the reduction of the L. For example, if L is so small, can you see we can end up with this situation? You know, when L is this large, it really doesn't matter what L is, right? Is that correct? But at some L, the barrier is now smaller than before now. Can you see that? You don't see it? All right, let me draw it again, okay? I'm looking at a case at a VFB just because it's easier, the barrier is larger to see. I'll start with VG equal to 0. Let's start with that, okay? With VG equal to 0, we have 0.5 volt of barrier. Is that right? And this is VDS. Is that correct? Now I'll make the channel length smaller. I end up with this diagram. Is that correct? Did that reduce this barrier height? Still 0.5 volt, right? But if I make the gate length even smaller, at some point we'll get something like this, won't we? Won't we? That's called drain-induced barrier lowering. It's as simple as that. All right? By the way, if you get to a case just like this now, you don't have any barrier at all. You could call it punch-through, right? But we'll get to that punch-through later, add some more words. But right now, let's stop at barrier lowering. Can you appreciate this name, drain-induced barrier lowering now? All right. So the threshold has a lot to do with presence of barrier. VG is supposed to, the parameter to reduce the barrier. Nothing else supposed to change the barrier. But in reality, shortening the gate channel length can reduce the barrier. In other words, the drain can reduce the barrier. We call that drain-induced barrier. All right? By moving the drain very close to the source, reduce the barrier. Okay, that's called drain-induced barrier lowering. So we'll start with this next time. All right?